So we're continuing on here. Last time we talked about measurements and really density. Reminder, right? Density is our mass divided by volume. We do need to be able to obviously rearrange and solve for any of the other ones. So volume would be mass divided by density, while mass would be volume times density. We also talked about different ways that you could get the volume of a solution. Obviously, you could take a reading. If you're doing some type of length measurements, you take the length times the width times the height and convert that into a volume. And more importantly as well, like you did in that lab, volume by displacement is a very common way that we can sort of determine the volume of an object by taking the final volume minus the initial volume. Gives us the volume of the object that we are sort of looking for. So it's a very, very common way that we could do that. We also finished up talking about, or started to talk about, really, as we mentioned, how they want you to really perform sort of calculations in chemistry as you go through the different classes. And that is really the dimensional analysis approach, where we use conversion factors and we use different units to sort of convert everything. So, you know, if we're going from, say, unit A to unit B, we would use a conversion factor, which is what this would be. We put the units in opposite locations so that they cancel. If we want to go one more sort of unit, we could again go with units A, B to unit C, again, canceling. Once again, what we are doing here is we're multiplying across the top and coming back and dividing across the bottom. So these are all ways that you should show all your work. And when they say show your work in chemistry, this is really what they want you to show using those units. We do get conversion factors, obviously, from equalities, right? And equalities are basically two values that are on different unit scales, but they do represent the same amount of something. Obviously, like 12 inches is 1 foot or something of that nature. Any questions on any of that stuff there? Okay. So let's talk about the general steps here of working out really dimensional analysis sort of problems. Thank you. First off, it's really important to write sort of what's given to you in the problem. It's also very helpful to write what you're looking to find. Any type of equalities, obviously, that would be appropriate in this type of conversion. The conversion factors that go along with that. Really, the most important thing in all the work that you do in chemistry classes is number 5, is to really set up the calculation where you see all the units canceling and everything like that, like I just demonstrated there on the last page. And then obviously you should solve it to the correct number of sort of sig figs, right? So a couple of reminders. Also, I think talked about that last time. When we multiply and divide, we do look at significant figures for our answer, and is the one with the least number of significant figures is how many significant figures your answer should have. When we add and subtract, we're looking at decimal places, so it is the smallest number of decimal places is what your answer should have. Again, if you do some type of combination of those things, you do need to kind of keep track of all the steps that you do, and you really want to clean it up there at the very end to the right number of sig figs. In addition, forget what I was going to say, but in addition, you should do something else maybe with that calculation. It'll come to me, I suppose. That's what it was. Obviously, if we do some type of conversion that it uses what is considered an exact number, which we also, I think, talked about as well last time. Remember, exact numbers are really two things. They're either things that are counted, or they are those sort of definitions, like 12 inches is a foot. Those guys can have unlimited number of significant figures. So we do sort of ignore their contribution when we're trying to determine how much sig figs our answer should have. The one place where you really should look at it, though, is if you happen to, again, use a conversion factor that is sort of metric to English, and it's not like the 1 inch is 2.54 centimeters, you know, any of those guys. Once again, you should technically look at that conversion factor and use the sig figs if necessary. So So obviously, if we look at this pretty straightforward, simple sort of problem here, if we were looking for how many pennies there would be in $1 or $3, we would use our equality, which $1 is 100 pennies. Again, from each of that equalities, you could write two conversion factors. So clearly, if we were to do this calculation, we would start with our $3. Again, we want to set it up where we can see everything canceling. It is not written as a fraction, but it's assumed that the dollars are essentially up on top. So we want to go opposite to cancel that. So that is going to be that guy right there. And that will get us 100 pennies is $1. Yeah. That went the backwards there. Let's try that again. Set up the conversion correctly would be good. Let's try that again one more time here. Give it the old college try. We want to go opposite, so dollars would be on the bottom there. There we go. And 100 pennies up on top. Dollars will cancel. We will multiply across the top. In this case, nothing really to divide there on the bottom would give us 300 pennies, really, in this case. In terms of significant figures, obviously the 100 pennies and $1 would be considered an exact number. So really the only thing we got really to play with here is the $3. So we could leave it at one significant figure like we did there. Without the decimal point, would leave it at one significant figure. Any questions on that there? All right, so let's try one here, or why don't you give it a try? Go to the AM PM, you get yourself a 32 fluid ounce drink of Diet Coke from the Thirst Oasis. Too much good stuff. How many gallons of Diet Coke did you drink? Here are some equalities and some conversion factors that might be helpful in this problem. So give it a second, set it up so you can see the units canceling, the dimensional analysis. Okay, let's take a look to see how we're doing. So clearly we would want to start with what was given to us, which would be the 32 fluid ounces. That is basically up on top. So we want to go opposite there to get rid of our fluid ounces. So we would want to use our conversion factor over here on the left to do so. This would give me 1 quart is 32 fluid ounces. If I stop the calculation right at this point, the fluid ounces on top and the fluid ounces on the bottom would cancel each other out. We would be left with units of quarts, which is close to what we want, but we do want gallons. So we want to go one more conversion. So our quarts are up on top. So to get rid of it, we do need to go opposite of it, which would be this guy here. This is going to give me 4 quarts is 1 gallon in this case. In this case, the quarts will cancel. Once again, we're going to multiply everything on top. So that's 32 times 1 times 1. You can come back and divide by 32 and divide by 4. That is going to give us 0.25 gallons in this case. For the most part, we got exact numbers in the middle, which means 32 is the only number we have going on, which is 2 sig figs, gives us 0.25, which would be 2 sig figs. The answer is 0.25. It is not 1/4. It makes me think you're just too lazy to divide. Yes. So you should never give an answer as a fraction. You should always divide it out and get yourself a decimal and stuff like that. Because I have seen people write something like, you know, the answer is 455 miles over 3,284 hours, and they box it. Yeah, so that is not the right thing to do. So you usually never leave it in a fraction, divide it out, get a number to a right decimal place or right decimal type number and to the right sig figs. Any questions on that one there? All right. Do you need to show everything that is here? The answer is no, but if you want all the points, you got to show all that, yeah, on the bottom, set up like that with the units and everything canceling. Any questions on that? All right, so let's try another one here. We got a antibiotic dose is 500 milligrams is ordered. It comes as 250 milligrams in 5 milliliters. How many milliliters would be given? Okay, so let's take a look where we should end up with this. So very often in problems, much like this, we kind of get a conversion factor sort of given to us in the problem. And obviously we could use that as one of these two versions here as a conversion factor. We have 500 milligrams, so that is definitely where we would want to start. So we got 500 milligrams. Guess the dot got lost there. Once again, we're going to do opposites to cancel. So we're going to use the conversion factor there on the right to do so. That will give me 5 milliliters over 250 milligrams. Once again, the milligrams here will cancel. We're going to take 500 times 5 divided by 250, going to yield us 10 milliliters, I believe, in this case. Any questions on that one? Now, in this particular case, the 250 milligrams per 5 milliliters is not a true equality, right? A true definition. Happens to be specific for this problem. So we would look at the sig figs here, and that's both has 2. So that is why we would end up with 2 in this case. Any questions on that there? It is why I put the decimal. Yeah, so without the decimal, it would have just 1, right? And obviously, if I put an extra 0 here, you would have to do that. The other way you could do it is obviously scientific notation as well. You could do 1.0 times 10 to the 1 if you really want to. Other questions on that? All right, let's see here. How many milliliters of plasma are we getting here? In 5 pints. Okay, so taking a look at this one here, we got 5 pints. We want to go to milliliters. So again, this could be a pathway to get us there, those 2 equalities. Those are obviously the conversion factors we could get from each of those equalities. So we'll start with what was given, which was the 5 pints. Once again, we're going to do some opposites here. So we first want to get rid of pints. So that will work for our opposite location. 1 quart, 2 pints. Once again, if we stop right here, the pints will cancel. We will be left with quarts. We need to go 1 more to get us to milliliters. And that would mean we would need to use our conversion factor on the right there. Since the units are in the proper places, we will set it up 1 quart on the bottom, 946 milliliters up on top. The quarts will cancel. Here we're going to multiply the 5 times the 946, come back and divide it by 2, going to yield us a 2365 milliliters on our calculator. Should end up where? Yeah, so really kind of looking at this guy here is really going to probably be the one that determines that. That's 2 significant figures. So that really should end up at 2,400 milliliters. Or once again, you could do your scientific notation if you wanted to, which would be 3. And that also would be 2 significant figures. So either way, but we should go up to the 2,400 in this case. Any questions on that there? So let's try one more here. See our conversion works. All right, you are stranded about 125 miles away from home. You decide it's nice and 140 degrees outside. Let's take a nice walk, and we'll walk it home. If you walk 55 feet per minute, how many days is it going to take you to get home? Provided you don't stop and you make it in one piece, I suppose. Yeah. All right, take a couple minutes to see what you come up with here. So let's take a look. So in this case, we basically have 2 things going on. We have a distance, which is our 125 miles. We also have really a rate here. And that rate is going to allow us, obviously, to go from really distance or length, if you will, to time, which is ultimately what we're looking for, which is days. We do have a little bit of an issue in terms of units. We got this guy, which is in miles, and that one obviously is in feet, so we could not use them together at this point. We do have to do a conversion. You got to convert either the feet to the miles or the miles to the feet before you could really use them together. I personally am going to go with the miles to the feet approach. So that would be my first conversion. I would take 125 miles. I will convert that into feet. So there's 5,280 feet in a mile. Miles will cancel, lays us up something like 660,000 feet. It's a good walk. At this point, we have really our distance there in feet. We now have our rate in feet per minute. So we could really use the rate as a conversion factor. So we could really use it one of two ways. We could use it like it's written there as 55 feet per minute. We also, if we needed to, could flip it around and go with a minute is 55 feet. And that actually is the way we do want to use it here so that the units cancel. We would take our 660 there, feet. We would use our rate as a conversion factor, which would give us our 55 feet per minute. That part there is going to get rid of feet, and that's going to convert it into minutes, which is a unit of time. And hopefully we do know these, right? So we will get rid of our minutes. There is in a minute, there are 60 minutes in 1 hour. So our minutes will cancel, and we do want to end up with days. So there are only 24 hours in 1 day, and our hours again in opposite locations will cancel. That is something as crazy as it sounds that people screw up on. They go like 60 seconds in a minute, 60 minutes in an hour, and like 60 days and or 60 hours in a day, which is a lot of hours. So hopefully don't screw that up. We're going to multiply all the way across the top there, which is basically just the 660,000 times 1. We're going to come back, divide by the 55, divide by the 60, and divide by the 24, and that would give us 8.33 days. It's a long walk, I suppose. Any questions on that one there? That's really the purpose, yeah. So the purpose of why they make you do it this way is that's the way they want you to show work rather than just rando numbers on the page, right? And you know, who knows what went wrong. Lots of stuff go wrong between the calculation on the page and the calculator. So at least if you show this, you could get some points along the way is really the main reason. The other reason is a lot of times, maybe not in this situation, but where you have a number where maybe you're actually converting out 2 units, like, you know, miles per hour. Maybe you want to go to kilometers per second or something like that. People oftentimes lose track of like that bottom unit, like, hey, should I be multiplying? Should I be dividing? So if you set it up like this, you should be able to clearly see, you know, should you be dividing that number? Should you be multiplying that number? And there are chemistry like molarity, for example, which is actually moles per liter. When people use just the molarity symbol, which is just big M, they have absolutely no clue where the liters part should go, where it's at, and stuff like that. So, like really showing all these units this way, you hopefully get a catch. So, you know, make sure you know you should be multiplying and dividing. No, you can do that as part of it. I just personally just did it separate. Okay. So here's the rule. Here's the deal on this. The way they want you to learn it these days is they want you to do everything in one long calculation. Yeah, just one right after the other, basically. I personally don't really care which way you do it. Some people will do one step, get an answer, take that one, do the next conversion, get an answer, do the next one. They technically, for some reason, don't want you to do it that way. If you do it in parts, technically, like we talked about, you shouldn't round, obviously, until the end. But they really want you to set it up all the way. And you could have incorporated that very first step here as well. Yeah. Okay. Yeah. So here's the good news about, here's sort of the good news about this type of calculation. Just straight up multiplying and dividing, right? So that's the only math that you're doing. So you're going to be looking at significant figures, right? Now, when we look at significant figures, really a conversion factor, so we can ignore it because it's an exact number. Really a conversion factor, you can ignore it. It's an exact number. You don't have to take that into account. So really what that leaves us in terms of numbers that we really should look at in this particular problem would be this one because it came from the problem. It's not like 12 inches a foot always. This has got 3 significant figures, right? My original number had 3 significant figures, even though technically I didn't go 3 sig figs on that. I just took the whole number. So that is why we should actually end up with 3 significant figures in this particular case. I'm gonna say yes with a not a 100% of the time, but probably more times than not, that original number, if all you did was like a conversion, probably going to be pretty close to the right number of sig figs. So again, technically, you should be looking at the calculation part. Anything that is a for sure like metric to metric conversion factor that you use, like grams to kilograms in there in a calculation, that's an exact number you don't have to worry about. Anything where you did like English to English, like 12 inches is a foot, that also is an exact number about it. Where it crossed over from metric to English, other than they want you to know the 1 inch is 2.54 centimeters, that's considered exact. And I think she added there the 1 pound is 453.6 grams. But if you happen to have one, maybe on the last page we did quarts to milliliters or something, right? That technically is kind of a crossover conversion. You would look at that 946 in that last problem. So we wouldn't look at that one. We still look at the 2 sig. So I would say probably a majority of the time that you do this, and it's not 100%, but a majority of the time that you do this, you could probably almost consider them exact numbers and default back to the original number. But in this case, you would have to look at this number as well. They should, yeah. Yeah, that was it, yeah. Yeah. So again, they want you to kind of know a lot of these things, yeah. So as we talked about at the beginning, they're like really cracking down on this class that you got to kind of know most of these. So I would anticipate most of it not being provided for you. If it's something maybe we didn't talk about or something maybe I think you might not know, I would provide it. But pretty much the instructions were like, give them a periodic table. That's sort of the instructions. So that tells you basically the role they're here. That's sort of what they want. So they kind of want you to know these sort of conversions. So as we've gone through a number of them here, I kind of boxed them and said, hey, these are ones you should know them. Definitely those prefixes, how to go from the kilo and centi and those type of things, you should know, and you should know formulas. So they really would want very, very little given to you because they do not give you a lot as you go into 1A and 1B and stuff like that. So they expect you to know those things kind of coming in. Other questions on that? Did I get everybody's questions? Yeah. So in terms of significant figures, like I mentioned before, for the most part, you're almost safe most of the time, more times than not. If you go with that first number, it's probably the right sig figs for the answer if all you did is conversions. But you should still look at it because there could be a conversion factor that you're using that you should look at. But probably a majority of the conversion factors you use would be considered an exact number, and you really can sort of ignore their contribution. But you should take a peek in case you happen to come across one that you're using that you should look at it. Other questions? All right, questions on dimensional analysis and showing the work. Once again, obviously, this stuff here is what you need to show, right? If it helps you to show the conversion factors and write them out like that, or the equalities, you could do that. But for full credit, you need to show the setup, obviously, with the units and the dimensional analysis and all that. Any questions on any of that there? All right. So I think for us, that wraps up now chapter 2, since we did density last. Okay, in chapter 3 here, we're going to talk about matter. We're going to talk about, again, the different states of matter. And we're going to talk about substances, mixtures, and all that fun stuff. So let's start with matter. Obviously, as we might have talked about at the very beginning, but in case we didn't, let's just make sure. There's obviously 3 states of matter that we commonly come across. There is the solid state, where everybody, again, is packed in pretty tight to one another. There's not a lot of room for movement. The atoms, molecules really can't pass one another as they go through it. We then have the liquid state, which again, they're still relatively close to one another, but there's a little bit more room for movement. They can pass each other. That's why liquids are obviously more fluid than solids. And when we get to the gas state, that's basically where everybody has broken apart from one another. They're flying around. As we'll talk about when we get to the sort of the gas chapter, those collisions with the container and stuff causes pressure that we associate with gases. Some of the important transitions between these different states are really physical changes that we'll talk a little bit about here in this chapter and a little bit more later. But a reminder that if you go from solid to liquid, that is the process of melting. You go from liquid to solid, that is the process of freezing. Going from liquid to gas, that's the process of evaporation or vaporization. Going from gas back to liquid, that is the process of condensation. You could also go from solid directly to the gas phase, again, sort of skipping the whole liquid mess, and that is your sublimation. That is what dry ice does, right? By the way, dry ice is not water, it is carbon dioxide. We could also go the opposite way from gas back to solid, skipping the liquid phase. That is what is known as deposition. A lot of what we study in chemistry does involve these different states, these sort of transitions from one state to the next. In addition, the energy is sort of related to these transitions. And we're going to talk about energy in the next chapter we talk about. But just in general, as you go from solid to liquid to gas, you do need to put energy in to do that, right? So say if you have an ice cube, it needs to absorb the energy and start to melt. And that are processes which are known as endothermic. That is energy absorbed. Going the opposite way, starting with gas to liquid to solid, we actually need to remove the energy from those systems. So if you think about gas molecules flying around, if you remove the energy, they're going to slow down. So when they come in contact with each other, they are going to basically stick, not really be able to escape one another. If you continue to take out the energy, like if you put liquid water in the freezer, all the energy will release from the liquid water. And those are exothermic processes. And that is when energy is released. Now, when we think about the process of melting and freezing, they actually do occur at the exact same temperature. So when we talk about melting and freezing, it's the normal melting point or boiling point, melting point or freezing point of a substance. And the normal melting point or freezing point of the substance is where that process occurs at exactly that temperature. So for water, that's 0 degrees Celsius where that occurs. You actually have both phases happening at the same time. You got some solid, you got a little bit of liquid, you got like ice crystals sort of happening. It's not till you get a little bit above 0 degrees that you get liquid water, not till a little bit below 0 degrees that you do get ice. So they actually do occur at the exact same temperature. Same thing with the evaporation and vaporization and condensation. These two guys also occur at the exact same temperature. That would be the normal boiling point for a substance. And for something like water, it's 100 degrees. So exactly at 100 degrees Celsius, again, you have kind of both phases happening at once. You have the liquid there, and you also have some steam or gas version of that particular substance. What determines sort of which way you go at that point is what you're doing with energy. If you put energy in, you will continue the process of going from solid to liquid to gas and those transitions. If at those points you continue to take the energy out, you will go the opposite way, go from like gas to liquid to solid. Any questions on that there? So matter is pretty much anything that occupies space and has mass, which is pretty much everything. Solid, as we just saw there, has a definite shape, and it's very hard to change the shape of it. Is sometimes referred to as being very rigid. And again, because they really don't have a ton of energy, so they just kind of lock into place, and they're very close to one another. One exception of that would be water. Water is an unusual substance. Actually, in its solid phase, it's less dense than its liquid counterpart. That's why when we put ice in our cup, it floats to the top. And that's because when water comes together, it creates a lot of empty spots and volume between the different water molecules. And that makes the density actually in solid less than it is in the liquid. But most substances is sort of the opposite. Liquid, on the other hand, does not have a definite shape, but it does have a definite volume. And what that means is if you had 5 milliliters of water and you put it in the trash can, it would take the shape of the trash can. If you put it into a water bottle, it would take the shape of a water bottle. If you put it into like a silly straw, it would obviously take the shape of the silly straw. What it means in terms of definite volume is if you started with 5 milliliters of water and all you did was move it from one sort of container to the next, and you weren't a klutz and spilled it all over the place, you should still have 5 milliliters of water as you go from one place to the next. Gases, on the other hand, they have really the shape of the container. They do take the shape of the container, and we think about them as filling the container uniformly. And when we talk about gases, and you'll talk more about gases later on in the next class as well, but we'll talk about gases as well. There is the ideal gas, which is typically what we think about of an ideal gas. And one of the things that makes something an ideal gas is because we anticipate that most gases will behave ideally. They will fill the container uniformly. So when we look at the volume of a gas, oftentimes we refer to the volume of the gas as actually the volume of the container rather than the volume of the gas molecules that are flying around in it. And that's because, again, it's assumed that they are basically uniformly kind of filling the container as they fly around. So the entire volume of the container is essentially the volume of the gas in an ideal gas. In a real gas, not so much, but in a ideal gas situation, that is typically what we look at. So here's obviously liquid in its different shapes that it will take as it fills a container. Here's our water and the different states of water, our solid, our liquid, and our gas. And this is what I was talking about. When water comes together, it has all this open space between the different water molecules. As we'll talk about in a later chapter, water basically comes together and is held together with each other through what is known as hydrogen bonding. So when these hydrogen bondings come together and they make these hydrogen bonds, the water molecules basically spread out. And since density, once again, is mass divided by volume, that's going to increase the volume and make the density less. By the way, all three of these things, they are essentially all H2O, right? So as we go from solid to liquid to gas, as we'll talk about, these are, as we will see, physical changes, right? These are not chemical changes because they're fundamentally all still water. They just have a different appearance, and that is definitely a physical change. So sometimes people think when they boil water and they see the steam, it's gone through a chemical reaction or a chemical change, and it hasn't. It's still obviously still fundamentally H2O. Any questions on that there? So here, again, some of the stuff that we talked about in terms of definitions of solid, liquid, and gas, and some example. The ultimate sort of thing that determines a lot of times what sort of state a substance is in is a type of force that we will talk about in a later chapter as well, which is referred to as a intermolecular force. And it really is sort of the force that holds basically two molecules together. So it is the force that basically will hold a water molecule together with another water molecule. It is the force that will hold a methane molecule together with another methane molecule. And those intermolecular forces are really the ones that determine a lot of times what state things are in. If you have something that is held together in terms of molecule to molecule by a really strong intermolecular force. That means, typically speaking, it's a lot harder for that guy to get into the gas phase, right? Because in order for that guy to get to the gas phase, you got to break the bond between the two molecules, right? So they can separate out and start flying around. So if they're held together by a really strong force, it is a lot harder for it to go into the gas phase. What that usually results in is those things have a much higher boiling point. So it takes a lot more energy to kind of pull them apart from each other. If you have two molecules that are basically held together by a force that is super weak, it doesn't take a lot of convincing for those guys to kind of break apart from each other and go into the gas phase. So sometimes you hear the word volatile, or this thing is a volatile liquid or something like that. And what that means is it's able to kind of go into the gas phase really, really easily without a lot of convincing. And that's because it's held together by a very strong, a very weak intermolecular force between them. There are certain things that are held together by really, really weak intermolecular forces, which typically in normal cases are going to be gases, like when you light your Bunsen burner today. That is the methane coming out. Methane is a gas. Methane is a nonpolar molecule. It's held together by the weakest known intermolecular forces. So it has found itself in a normal situation as just being a gas or normal conditions because it's held together by a super weak sort of force. So these things affect, as we'll talk about more in depth in a later chapter, they affect things like melting points, freezing points, boiling points, how strong two guys are held together. Again, typically speaking, the stronger something is held together, the less likely it would exist as a gas under normal conditions. So now we're going to talk a little bit about physical and chemical properties and changes. A physical property is one that can be measured and observed without changing really the composition of that substance. Typical sort of physical properties: odor, color, volume. Most common thing we come across a lot are what we've been talking about, the different states of matter. Is the thing a solid? Is it a liquid? Is it a gas? Things like density, melting points, and boiling points are all physical properties that you can measure about the physical characteristics of a substance. Typically, physical properties relate well to physical changes. And basically, with a physical change, what you start with and end with are fundamentally the same thing. So they are fundamentally the same thing when you go through a physical change. Perhaps something looks different. So the example would be really the water example, for example, we just talked about. As we go from ice to liquid water to steam, they are all fundamentally still H2O. They are all still the same thing, although they may look different. There is no chemical change happening here. Those are all physical type changes. If you take a piece of paper and you rip it up, still paper, just in a million different pieces, right? You have a shirt you iron, still a shirt, less wrinkles, right? So anything where whatever you start with and whatever you end with, if you do something to it and it's still fundamentally the exact same thing, again, may appear differently, look differently, those are physical changes. Most common physical changes, again, in chemistry that we deal with is when those transitions from one state to the next, going from solid to liquid to gas. Any questions on that there? So there's that example with the water. We could measure something like the melting point, which is a physical property of ice. And as the ice starts to melt, it is again a physical change that's occurring as the ice again is still H2O. Now that is different than a chemical property. A chemical property is basically a property of a substance with its ability to go through a chemical reaction or change, or even the ability of that substance to resist some type of chemical reaction or chemical change. So chemical properties definitely relate to chemical changes, and chemical changes basically are different than physical changes because whatever you start with will change to something new or something different when the reaction is over. So in a chemical change, what you start with really and what you end up with are fundamentally two different things. The other really important part about a chemical change is this: you cannot get back your original substance by any type of physical means. So you can't like freeze it, can't boil it to get it back, you can't filter it to get it back. So there has been a fundamental change that occurs. Rust, for example, is an example of a chemical change. Rust basically is iron and a little bit of oxygen gas. They come together, make a little iron 3 oxide, and they're fused together. You can do as much as you want with that rust. Pull it off, throw it in the freezer. You're not gonna get the iron back. You can probably even heat it up. It probably won't give you the iron back or anything like that. You're just gonna, you really can't get those things back. When we make water from hydrogen and oxygen gas, to make water, we take some hydrogen plus some oxygen, and we can make some water, a little balancing like I'm in chemistry class here. There we go. I'll do a little bit of that action there. So we have hydrogen gas and oxygen gas, which by themselves will come together and make water. And that is definitely a chemical change. Once again, you put the water in the freezer, you can make ice, it's still water. Not gonna get the hydrogen gas or oxygen gas back. As we maybe know, if we made pasta, right? If you boil water, you don't get hydrogen gas or oxygen gas back. Otherwise, you really don't get to the part where you dump the pasta into the water, probably. You don't get those gases that are formed. So the only way you could get those guys back would be you would have to do some type of chemical change or chemical reaction to it. You could run an electrical current across water and you will get back the hydrogen gas and oxygen gas. We'll do that in a lab coming up shortly. Take a 9-volt battery, do a little electrolysis there of water, and you'll produce hydrogen gas and oxygen gas. So physical change, what you start, what you end, basically the same thing. May look different. Chemical change, what you start with, what you end with, definitely something different, and you really can't get those things back. So that's the example, obviously, of the making of water. And again, any type of physical process you try will not get you back those original substances. Making a hard-boiled egg, again, as you kind of cook the egg, it will undergo a lot of chemical reactions. Then when we eat it, or anything else that we eat, obviously our stomach breaks everything down, right? And through chemical reactions and chemical changes, where, as gross as it sounds, you probably don't want any of that back, I imagine, at any point. So a summary of the physical and chemical changes. As I mentioned, physical changes, one or more physical properties are involved. Most common, solid to liquid to gas. Chemical changes definitely involve some type of fundamental change of what occurs. And those are usually referred to as chemical reactions. Silver picks up a little bit of sulfur, makes some tarnish through a chemical change. Also, in addition, usually the sort of elements that make up a sort of compound are usually very different, and we'll talk about that. But a lot of what you start with is usually very different than what you end up with in a chemical reaction. Fundamentally speaking, you know, they have very different properties as you make new things. Remember that all chemical reactions basically involve just a rearranging of bonds. So we do keep all the elements along the way in a chemical reaction or a chemical change, but things reunite in sort of different ways, which produce different compounds and substances. Any questions on that there? So let's talk a little about elements and compounds. Elements are basically the basic units by which everything is made up of. Got a periodic table, obviously, of all the elements that we have. We can think of elements as like the alphabet, and much like the alphabet, you can combine a lot of different letters to make a bunch of different words. So obviously, the combination of different elements will make different compounds along the way. Now, elements are basically made up of atoms, is the simplest representation of a element, and atoms, as we will talk about, have protons right? They have neutrons, most of them, and they have electrons. So the basic sort of representation of every element are the atoms. And when we talk about elements, though, they can actually be what are referred to as molecules. So most of the elements, as you see on the periodic table, they are what are referred to as being monoatomic, which means they basically come as one atom, basically. So if you had something like copper, it's just Cu. If you had something like iron, it's just Fe. But there are certain elements that come as twos, like the hydrogen that's there. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All these guys come as what are referred to as diatomic molecules. Diatomic means two, atomic means atoms. So they come as two atoms together. So if you have hydrogen by itself, uncombined, it is not just H, it is a couple of H's that are basically bound together. You have oxygen by itself, also comes as two oxygens together. These are what are referred to as molecules, and molecules have a basic definition of two or more atoms that have come together. Now, sometimes people get confused about a compound versus a molecule, but we'll start talking about molecule first. A molecule is just a simple definition of that. You need two or more atoms together. Those two or more atoms could be the same element, like in this case. They could also be more than one element together, and they are all molecules. So each of these listed here are considered molecules because they do meet the definition of molecules, but because they are all atoms of the same element, they are also considered elements. The one thing that these guys are not considered is actually compounds, because compounds are two or more atoms of different elements. So in order for something to be a compound, you got to at least have two or more different elements involved. So these are molecules because they have two atoms, but they are not going to be compounds. And they are still elements because all the atoms are the same element that is there. We could also have a molecule like this guy here, which would be water. This is a molecule because it has two or more atoms. This is not an element. So that is not an element because we have hydrogen and oxygen happening there. So it cannot be an element. So an element can only be the same element or atoms of the same element involved. It can never have more than one happening at it the same time. Yeah. All the noble gases are monoatomic as well. They come as ones. So pretty much what I just boxed there are the only elements that come pretty much as twos. Yeah. So if you have any of those elements by themselves, those are the proper formulas for which you should write. The other important thing is when we take somebody off the periodic table, they really don't have charges. So sometimes people think, and then we learn about naming and charges and all that type of stuff. They don't have charges. So if you had just a piece of copper metal, it has no charge. Things will really only get charged when they combine. So when typically a metal and a non-metal come together, that's when things actually pick up charges. But if you had just an element by itself, uncombined with anything else, it would not have a charge or anything like that. So that's another thing sometimes people mistake on there when they write formulas. So let's talk a little about those things. So we just talked about our molecules, which again are two or more atoms together. A compound, on the other hand, is two or more atoms of different elements. So you got to have those different elements. So again, the water example, the methane example, which would be this. These are all compounds. They're actually both molecules, but neither one of those could be elements, obviously, because there are obviously multiple elements involved. Again, like we had before, our H2 or O2. These both are elements, and these guys are molecules, but they are not compounds. So again, a very time people get confused about those two type of things. Now, usually you can break down compounds to the elements by some type of chemical change or chemical reaction. But once you get to the elements, that's basically as far back as you could go. In addition, right, the elements that make up compounds, for example, usually have very different properties than the compounds that they make. So for example, if we look at, say, salt, for example, a little bit of sodium metal, a little bit of chlorine gas, not that, there we go, chlorine gas, makes a little sodium chloride action. Again, we'll do the right chemistry action there. So sodium metal is like a soft metal, cut it with a butter knife. Chlorine is a toxic green gas, which we probably wouldn't want to put it on our fries, right? But the miracle of chemistry is we can make salt. It goes very nice with fries, right? And all that good stuff. So good job, chemistry, right? But very, very different properties, obviously, than what makes up. Same thing with the water example, obviously hydrogen gas and oxygen gas. Very, very different properties, explosive type properties versus, say, water, which is pretty safe to use, right? So very, very different, usually the properties of the elements that make up those compounds than the properties of the compounds themselves. As I mentioned, you definitely could go from compounds through some type of chemical change, chemical reaction to get back those elements. And again, you'll do it in a week or so, I think. Again, running that electrical current over water will allow you to break apart that compound of water into hydrogen gas and oxygen gas, which are, again, the elemental version of it. When somebody says, like, I'm using molecular hydrogen or molecular oxygen or elemental hydrogen or elemental oxygen, that's a fancy way of saying I'm just using hydrogen and oxygen by itself. So you would write H2, O2, and things like that. Any questions on any of that there? Right. The next thing we're going to talk about is mixtures and substances. A substance is really any form of matter where, frankly, you have just one type of substance present. So, for example, if I had just pure water, that would be a substance. Just pure ammonia, which is NH3, that would also be a substance. Usually substances can be told apart by different physical properties, appearance, smell, taste. Don't do any of those things in the lab, right? But if you've ever smelled like ammonia, it's kind of like the Windex smell. And you smelled water, there's a very, very big difference. But a lot of times, a lot of substances, if they're liquids, they may actually look the same, right? A lot of liquids in the test tubes are all colorless, right? They all kind of look like water, but again, they may not be water. If you tasted something like vinegar, which is acetic acid, tastes very different than what water tastes like. So a mixture is really a combination of two or more substances. And the important part of that is the actual substances retain their identity. So even though it may look to us that they look different, that something disappeared, they are still there, even though we may not be able to see it. So an example of this would be if we took some water, which would be a pure substance. We took some solid sodium chloride, like you're going to do today, which would also be a pure substance. And if we put the sodium chloride, which is salt, in the water, the sodium chloride should dissolve, and we will get a sodium chloride solution or salt solution. And that's what the aqueous means here. AQ is aqueous, basically means a water sort of environment. And that is a mixture. Salt water, when you look at it, right, looks the same throughout. Can't tell if there's salt in there. I guess you did it right. If you took some water from the sea, just got water from the ocean, nothing else floating in it, no bodies, no anything else floating in the ocean there. It would just look like water, right? You taste it though. Obviously, it's a salt and maybe some other stuff floating in that water. There's different types of mixtures. Two major types of mixtures that we talk about are homogeneous and heterogeneous mixtures. A homogeneous mixture is like the saltwater example. You basically mix it, and after sufficient mixing, everything looks the same throughout. So it looks like kind of one phase sometimes people talk about, or one layer. Like the saltwater example, the salt will dissolve. Does the salt really go away? It doesn't. We just visually can't see it because it's surrounded by a ton of water. So it just kind of disappears from our vision, but it's actually still there, as you will see today in lab. Sugar, same example. If you take some sugar, you can dissolve it in water. It definitely will dissolve, no problem. The other type of mixture is a heterogeneous mixture. In a heterogeneous mixture, you can mix that all day and pretty much it will not really dissolve in each other. You will still see different layers, different phases. For example, if you take some sand and water like you're going to do today, once again, you can mix that all day. That sand is never going to dissolve in the water. You will always see the sand. So that is a heterogeneous mixture. If you have some chocolate chip cookies, hey, you see the chocolate chips. So that is a much better heterogeneous mixture, right? You should really do that lab instead. But you definitely can see the chocolate chips, obviously, in the cookies. So you can see these different layers. The important part, though, is regardless of if it's a heterogeneous mixture or a homogeneous mixture, you could actually separate out all the components of those mixtures by some type of physical means. So you could boil it, you could filter it like you're going to do today, you could freeze it or some other type of physical way. You could separate out those mixtures back into their original sort of form. So just to illustrate that, we'll use the example you're going to do in lab today, which is you will eventually make a beaker that has salt water, which is obviously a combination of salt and water. And you got some sand. I'm not sure why it's blue, but it'll be blue in this example here. First off, the mixture between the salt water and the sand is what type of mixture? It is a heterogeneous, right? Because you can see the sand in the salt water. The salt water by itself is what type of mixture? Homogeneous mixture, right? Because you can't really see it. So if we wanted to get out all these components here, we could do very simple processes, much like what you're going to do in class. We could take a process known as filtration, right? We could hook up a nice little funnel, much better than the funnel I drew earlier this morning. Put a little piece of filter paper up there, right? And dump it in, right? As I dump it in, on the filter paper should go wet. What should end up there? The sand, right? So the sand should end up on the filter paper. The liquid salt water should go through here. So in this case, by just this very simple process of filtration, which is a physical process, we're able to filter out the sand and we could let it dry out, right? And we would have sand just like it started, right? In its original sort of form. We have our salt water, which again is still a mixture. Salt water at this point is still a homogeneous mixture. So one way we could do it, which is a little different than what you're going to do, we could throw it into a terribly drawn apparatus such as this. Kind of a closed container, kind of with a flask on both sides. That's what they use on both sides, are their flasks. You have this little chamber here that connects them both. And this is usually kept super cold. Run some cold water through it or something like that. So if you put your saltwater mixture on this side, and I decide to start to heat it with my wonderfully drawn Bunsen burner, which is also known as a triangle on the line. As I start heating this thing here, right, what's going to happen to salt water? The water part of it is going to start to evaporate, right? So as the water starts to evaporate, it's going to create steam, which the steam is kind of trapped, so it's got nowhere to go. So when we have steam, which is the gas version of water, goes through this very cold section. What happens to gas when it gets cold? It goes through condensation, yeah? So it loses energy, goes through condensation, and out dripping on this side will be your water, right? And you continue this process of heating the left-hand side until you pretty much have evaporated off all of the water. Try not to erase my entire thing here. There we go. And what you will be left with on the left-hand side, you probably should shut the gas at this point, but you'll be left with just the salt on the left-hand side, right? And now we have successfully separated out the salt from the water. And now we have all three of our components in this mixture. We have the water in its liquid form like it originally came. We could let the salt dry out. We would have the salt in its original form, and we have the sand in its original form. Any questions on that? This process here is what's known as distillation. What you're going to do in lab is kind of the same idea, except you're going to use an evaporating dish. And as you put your salt water in there and you heat it up, all the water is just going to go out into the environment. So you're not going to collect it. You're just going to let it evaporate off. What will be left in your evaporating dish will be the salt. Because I'm able to get all these guys back in its original sort of form. Here's, worst picture if you want to look at this picture of distillation. I really think my artist's rendition was much better. But you could look at this and the same idea here. Because I was able to get all of the parts of the mixtures back in their original form, is a mixture a physical change or a chemical change? It is a physical change. We cannot see the salt anymore because, like I said, in a way, salt dissolves, as we'll talk about in a later chapter, pretty much gets surrounded by tons of water molecules, which visually we can no longer see it. What we're really doing in these type of procedures here is we're taking advantage of physical properties of these things. Because water and salt's an ionic compound, super strong attractive force holds that together. Super large amount of energy needed to get that to boil. Doesn't happen in normal conditions. So it'll start to melt before it'll boil. Water, though, you just got to get to 100 degrees. So using the differences in those physical properties allows us to heat it up and get the water to come off, but leave really the salt intact by itself. So we're taking advantage really of physical properties to allow us to separate these things out. Any questions on that? That is chapter 3. It's a good deal.